Our next speaker is Igor. He's engineer at the Technology Innovation Institute, the Department of Propulsion and Space Research Center, right? So Igor, the floor is yours. Please share your
Hi
screen.
everyone. Hi everyone. Can you see my screen?
Not yet.
Not yet.
No.
All right. Let me try again.
Okay. Yeah.
How about now?
We see
All
it.
right. All right. Perfect. Hi everyone. My name is Igor. I'm an electric propulsion diagnostics engineer at the Technology Innovation Institute in Abu Dhabi. Today I'll tell you about our upcoming facilities for testing space engines for satellites, electric propulsion engines, and about our research in modeling their plumes of those engines. Well, yeah, actually, my second slide is pretty similar to the one that Sultan showed. Thank you very much, Sultan, for a great overview of the TII activities. So, yeah, just to kind of remind, to recap, we are coming from the Technology Innovation Institute, which is a part of the ATRC, like a larger organization. There is also Aspire for program management and Venture One as a subsidiaries of the ATRC. And in total, we have 1,000 employees or so. And Technology Innovation Institute is essentially doing applied research for the ATRC. Moving on to space electric propulsion in the TII. Well, overall, electric propulsion is about those engines which are used on satellites in space. They cannot be used like as the rocket ones, as the chemical ones to lift it up from the ground. Yes, that's why they need a vacuum environment, like orbit-like, to operate. And in TII, and that's why they need chambers. And in TII, this whole effort of building the testing facility started in 2022 as a part of Space Exploration Vertical of Propulsion and Space Research Center. Our main goal is to build a new electric propulsion testing center in Abu Dhabi. Thus giving a solid start for this direction in the local ecosystem and serving global customers. So far, 3 chambers are planned, a single small one for cathodes and small thrusters, and 2 big ones for thrusters up to 5 kilowatts. Diameter of big chamber is going to be 3 meters, length is about 7 meters, and pumping speed up to 120,000 liters per second, thus allowing for testing powerful thrusters. We planning to launch those chambers in late 2026. As a part of design of diagnostics and measurement system for the facility, we're working on modeling of thruster's plume and how it interacts with vacuum chamber and spacecraft surface. Actually, we presented our model, the results and the model at the International Electric Propulsion Conference in London, which happened less than 2 weeks ago, or like 2 weeks ago. So far, as far as we are waiting for the chambers, still we want to make the model verifiable, and we trying to reproduce the case published in open source literature tests of the Safran's PPS 5000 Hall effect thruster in Aerospatiale Large Vacuum Testing Facility. This paper published in 2022 provided us with measured profiles of ion current density, plasma potential, electron density and electron temperature, as well as performance of the thruster at different operating points. And for this research, we chose the operating point number 8 as the one with the highest specific impulse, which might be of use for interplanetary space missions. Yeah, you can check the mathematical apparatus for which we used for this research in our paper, which is under the reference number 5, which I will show in the end. To perform the simulation, we used a spacecraft plasma interaction system developed by Onera and Artenom from France. This is a state-of-the-art tool for plume simulations, and its main advantage is that its source code is publicly available, which allowed us to include our model of facility-neutral background in common simulation framework. The overall simulation setup looks like this. We imitating large vacuum testing facility of Aerospatio here. Plume model in simulation consists of 5 heavy species and electrons. 2 charge exchange reactions between a singly charged plume ion and neutral, and between doubly charged plume ion and neutral are considered. Facility neutral model is so far the simplest one. When all those particles impacted the wall are being re-emitted back into the volume of chamber as thermalized neutral particles, and in the volume then they can engage in charge exchange reactions, impact the walls, and be re-emitted back into the volume, or being absorbed at cryogenic surfaces like this. All heavy species are simulated using space particle and cell implementation and electron simulated through space fluid Maxwell-Boltzmann electron model with polytropic closure. Walls of the chamber are grounded at 0 potential. Mesh used in the simulation is generated by a GMSH tool. It consists of approximately 64,000 tetrahedrons. We have added some refined region close to the thruster to resolve better near-field plume. It's also important that all the facet normal vectors in the mesh are pointed to the computational volume to ensure proper neutral emission and reflection. To verify our approach, we've compared measured plume parameters with those computed numerically. We computed those profiles at the distance of 1 meter away from the thruster to imitate 1 meter arc, which was used to obtain the measurements. Blue profiles on the plots correspond to measurements. We presenting 2 simulation cases here. Green one includes charge exchange reactions of plume ions with plume neutrals, but does not consider facility neutral population. And thus, it's like it's simulating the situation which could have happened in the orbit, in the vacuum of orbit. The orange one considers the facility neutrals. Thus, it imitates the environment inside the vacuum chamber. Yeah, as we can see, all the profiles, ion current density, plasma potential, electron density, and electron temperature, they are wider where when thruster is tested in the environment with the facility neutrals, the orange one, which is due to more intensive charge exchange collision rate. Those profiles match better with the experiment, especially in the off-axis region. Close to the tails, where collisions dominate. On-axis widening of current density and electron density likely caused by too wide beam divergence angle. We're gonna fix it later. Computed electron temperature doesn't really match the measured one, because the measured one was obtained using the Dreiwitstein method, which is which is a method to obtain electron temperature from the measurements. And in our space simulations, electron Electrons are modeled as a Maxwell-Boltzmann fluid. Thus, computed profile should match with those measurements obtained from Maxwellian slope, feed to the Langmuir current voltage characteristics, and to some point it does. To show that we present an electron temperature profile for another 5 kilowatt thruster called P5A red dashed profile, where measurements were obtained like that. Yeah, and these are computed neutral fields obtained by the model. So essentially, it's showing the density of the neutral particles inside the vacuum chamber. And to compute that, we developed our own module, our own code, like upgrade to the SpaceTech software. So total neutral background consists of 3 different components: thruster plume neutrals, facility neutrals, and charge exchange fast neutrals. Total neutral pressure field is the highest closer to the impacting surfaces like chamber walls and to the thruster. Then it slowly reduces to the volume and drops to the pumping area. The main limitation of our facility model so far is the full thermalization of neutral flux and independence of emitted particles of the incident particle energy, but again, we're going to fix it later. So in future, we're definitely going to improve our plume physics model, complicate the simulation setup, and start plume spacecraft simulations, because so far we are simulating only a facility. Yeah, thus so far model captures key trends. We are able to develop our own upgrades for the source code of the spacecraft plasma interaction system. Yeah, we can see that presence of facility neutrals improves the results. Yeah, and we're going to continue upgrading the model. And overall, we are waiting for our chambers to come in 2026. And while we are waiting for it, we are developing our simulation capabilities to start as soon as those facilities arrive. This is the list of literature. Thank you so much for your attention. I'm ready to answer your questions.
Thank you so much, Yegor. Thank you so much.